All right. Okay, so we'll get started. Most of you guys should know by now that the universal pause thing happened. So I'm curious to know how this affects people's desire to stay on in this stuff. But so far, quite a lot of people have turned up, so pleasantly surprised. Cool. Okay. So yeah, and also just it's been weird, obviously, because like the homework has been talking about word embeddings, and we haven't really talked about what they are yet. So for those of you who've worked through the homework, which I assume is most of you, a lot of the stuff will maybe be obvious. Hopefully some of the stuff will help you understand exactly what we were doing in the assignment. Okay, so let's get started. Oops, sorry. Okay, so word embeddings. Oops, let me close the window. Okay, so basically what we're thinking of now is we had this language model that we constructed. In your head, you should think back to that sort of really freaky graph with all those colors and lines, and there was like a hidden layer with a nonlinear layer to it, and blah blah blah. So that was this thing called a neural language model. Actually, for those of you who are interested, the paper that this concept is based on, which I cited in one of the slides, it's actually a really readable paper, and it's I forgot now. It's like a few decades old, but it's a seminal paper. And what's interesting about it is that a lot of time is spent thinking about the computational issues with these types of models, right? And I feel like this is very different from statistics, which is what I'm more sort of used to, where you have a model and then you basically have some theory. With sort of machine learning, what you end up doing a lot of times is, you construct a model, there's some intuition, there's something sort of guiding principle behind why you might set up a model. But then a lot of it just comes down to like computation. How do you speed things up to make it actually, run in some, manageable time and take as much data in as possible. So I really recommend that paper. I think it's really, really well written, and just a fun read. Okay, so that's basically language models. The idea there is always, let's construct a language model. And what is a language model? That's just something that can predict the words as well as possible, right? And it turned out that in order to get sort of the state of the art at that time, they basically had to think of a way to represent words in this sort of high dimensional form. So already at that time, they were thinking about word embeddings, but like no one thought to just be like, oh, maybe these distributed representations of words actually can be useful on their own, right? So this is what a word embedding is. A word embedding basically, okay, so I use word embedding to mean different things. One of them, I just mean like the actual embeddings themselves, right? So I associate each word with an embedding. So a vector in R to the D. Alternatively, you can think of word embeddings as the actual model that's, creates these embeddings. So in this class, we're going to go through one and then sort of touch on this other type of model. So I'm going to use those things interchangeably, unfortunately. So bear with me on that. Okay, yeah, and so the key point, which I've brought up a few times now, is that essentially you basically just forget about being so accurate in terms of your language model. And then all you want to do is basically take in as much data as you can, and so you care about computational expediency. Okay, and so we'll sort of work through how that actually sort of ends up being this word-to-vec model. Okay, so the first thing we're going to do is we're going to scale back to a bigram model. Okay, so when we looked at the general neural language model, we had these n-grams. And then if you remember, what we had was like something like X was like a concatenation of C of like W n minus 1, C of W n minus 2, and so on and so forth, right? So so with that model, it becomes much more complicated. And so what they decided was like, okay, let's just forget about these n-grams. Let's just focus on bigram. Obviously, that makes this the simplest, right? Not only that, we're just going to get rid of the hyperbolic tangent nonlinearity. And then you might be thinking to yourself, well, if I get rid of this hyperbolic tangent, then like, isn't this model just like really straightforward? And we'll see, it actually is fairly straightforward, right? Because if you remember when we were describing sort of the very simple version of a neural language model, when we had just a bigram without the nonlinear component, it was basically like logistic regression, right? And we're going to see that's basically the same thing here. It's like basically a large scale logistic regression where you're sort of sharing the parameters for your input. So it's sort of a little bit clever in that sense. And then they're going to basically introduce these heuristics that are going to allow you to perform this algorithm, perform the SGD updates much faster. And the whole point of this is that, like, the simpler it is, the more data you can throw at it, the bigger the corpus of data you can run this on, and then you're basically done, right? So there's something to point out here, which may or may not be obvious. When you work with this type of data in the future, so if you're doing some NLP task, what's going to happen is you're going to basically deal with pre-trained models, right? Because ultimately, think about what's the product of these word embeddings, these word embedding models. It's just a representation, a vector representation. So like one of the key points is that, at least with this particular type of model, you only need to run this once, right? You can spend months running a model. Once you're done, you never have to run that model again because you have the vectors out already, right? So these types of word embeddings are, the key point is that, like, the state of the art word embedding models that people use, the ones that are pre-trained, sort of the scale of the data and the scale of the computation required to solve these things is such that you personally just don't do it yourself. You just deal with the pre-trained models, and those can be sort of just, you can just plug them into your algorithm or methodology that you want to use later on, right? So it's sort of nice in the sense that, like, this is not a case where you have some data and you have to fit it every single time you see new data. This is really just like a one-shot thing where you just do it once and you're done. Okay. Does that make sense? Any questions? Are there any open source libraries of word embeddings? Yes, so in general with these sort of state-of-the-art machine learning methods, the really nice thing is that almost all of it is open source. So off the top of my head, in R, I'm not that familiar with. In Python, there are, I want to say if you use something like GenSim, you can basically, it has all the pre-trained models, you can just download them pretty easily. In general, like you would, like if you just Google like R pre-trained glove embeddings, you will get something like that. I mean, so yeah, so I mean, for your homework, we basically downloaded it for you, but I'm sure you can find it. You might, at the very worst, you might need to convert the format into something that is useful in R. So the nice thing about this is that, yeah, all these stuff, it's come out from Google or academia, Facebook, maybe a little bit. They could have very easily made it all closed source, but thankfully, this whole literature is very, very open source, so you can play around with it at home and do whatever you want. Yeah. Okay. So yeah, so we're gonna basically walk through this, and hopefully, like, by going through this, then that will also help you understand the language model. So if we go back and think about what we're doing, so this was sort of the basic, well, this is not the basic one. So this is sort of the bigram neural language model, right? So key things to remember, basically what this is, you should think of this as sort of the softmax layer. Right, so whys here, one way, well, yes, right. So you just think of them as the whys that you're basically trying to estimate. Then what we're going to basically do is throw away basically any term that doesn't really matter. And so you basically are left with this guy here, right? So we're trying to make it as simple as possible without obviously making it sort of useless. So it ends up just being the y that you're going to estimate. So remember, what is y w2 given w1? That's saying, what's the score I want to assign to to guessing word 2 follows word 1, right? So if I think word 2 follows word 1 very often, I'm going to give this a high score. And literally the way I'm going to assign that value is basically taking an inner product between the word embeddings of word 2 and word 1. Okay. Something we talked about on Monday was that, like, in the general neural language model, you'll have two separate word embeddings, right? So whenever I say word embeddings, I just think of it as a map from my vocabulary to my word embedding space, so R to the D, right? And what we said before is that if we wanted to be more general, we would have a different embedding for the contexts and for the actual word I'm trying to predict. But that's obviously making it more complicated. So we're just going to scrap that and actually just have one word embedding shared across every single thing that we do, in this case, the words and the context, right? So essentially what I'm saying is that, yeah, all we need to learn now is that phi of W2, which is basically that C of W thing that we had before, right? So now I'm calling it phi, just to keep you guys on your toes, right? So yeah, so we've sort of like basically made it as simple as possible, right? It's like, what we're doing is we're, in order to assign probabilities to this bigram model, all we need to do is take inner products of the word vectors, the word embeddings, right? So if you think about it, what does that mean? That means that if you have two words that are going to be very close to each other, right? Or in other words, their inner product is going to be large, then that is equivalent to saying I'm going to assign a high probability to this, but the likelihood that W2 follows W1. Okay, and I just forget about everything else, like, forget about the bias terms. So the other terms they're basically parameters, right? You're going to learn those parameters in the neural language model through SGD and hopefully get a better prediction, a better likelihood, a better perplexity. Here I'm like, I just forget about it. Those are parameters I actually ultimately don't really care about, because all I care about is the embedding anyway, right? So okay, so literally that's what we do. So then the model ends up just being like this, right? So I mean, here I've just like replaced the y's with the actual values themselves. And we're not going to go through this calculation, but it's a very similar calculation to what we did when we looked at the class-based language models, right? So think back a week now, I guess. That was when we were thinking of clustering each word. And so we're trying to use, the probability that one cluster will then follow another cluster. That was what we're trying to do. Here, we're doing something a little bit different. Here, we're going to look at the actual word embeddings of the words themselves. And you can basically show that the likelihood here is going to have a very similar form, except now we're going to basically look at the average mutual information between the embedding vectors of your first word and the embedding vectors of the next word, right? So it's the same thing as what we had before. Remember what we had before was like C1 and C2 average mutual information. So the idea that, the intuition here is essentially saying it's the same thing. It's like I want to pick C1 and C2 such that C1 helps me to predict C2, right? And the same thing here, I want to pick these phi1 and phi2, which corresponds to the assignments I'm going to make for the vectors of the context and for the words, right? And then I want it to be such that knowing phi1 helps me to then guess phi2. Okay. So that is essentially the sort of the model form of this word2vec, right? So we're sort of trying to remove as much cruft as we can from the model of the neural language model to something that is as bare bones as possible, but still is able to capture relatively good prediction. Okay, so what we're going to do next, well, we've defined this model, right? Essentially, you're basically done, right? We've defined this model, we know the parameters, right? The parameters is that C matrix, or in this case, the phi, right? You can think of that as basically this matrix that stores all the word vectors, word embeddings, and then those are the parameters that I'm going to tune as I carry out this optimization, right? So I can just run SGD, and you're basically done, right? So you're not done, okay? But the model, that's essentially what the model is, right? So we're getting rid of all these things, and you basically do the same thing. You run SGD. But obviously, there are going to be some caveats, and then we're going to work through them in a little bit. So this is essentially the framework for thinking about what word2vec is doing, right? It's simplifying the language model and then running SGD. Obviously, with some twists to that story, which we'll talk about in a little bit. Before I go there, any questions so far? No questions. Cool. So you've seen this before, and you've seen this now in the homework. So this should just be a refresh, right? But essentially, what we're going to do is that we're going to basically try and get as much as we can out of a bigram model, but still cheat and try to like capture something like an n-gram model, right? Like, so this is what the skipgram is sort of doing, right? So if you think about the whole point of an n-gram model where n is larger than 2 is that you basically have sort of memory about what's happening before, right? So you can sort of take a combination of the words before to then help better predict the next word, right? Because like if you think about what a bigram model is, that's just saying, well, I'm only going to consider the previous word in predicting the next word, and so it seems sort of weird to do that, right? So here, what the heuristic that they're going to do is they're going to basically look at, you know, you said in the homework, is sort of like a window through which you construct your data, right? So all this is doing is augmenting your data set, right? Here, what I'm saying is that basically the context is going to be one thing, and then the things you're trying to predict is you're going to, you know, basically have the words around it. They're going to be the extra augment, like you're going to augment your data in that form, right? So here, the idea is that you're trying to predict the word swing, and your context usually would have been should, right? So if we were to look at the sentence, suppose the word you're trying to predict is swing. In a normal bigram model, you would use the should to then predict swing, right? But here, what's going to happen is that basically you're actually not going to just pick should, but pick the stuff around it. Okay. So it's like, you know, I mean, okay, so it's not like it's not an n-gram model, right? But it's not sort of a, you know, a vanilla bigram model now, because you've sort of allowed the data to be augmented in such a way that I don't care so much that, you know, the word should has to be followed by swing. What I care more about is just like the context around a particular word, right? So now it's sort of saying what I want to do is, you know, it's a little bit like a mini bag of words model here, right? So it's sort of saying, if I want to predict the word swing, I'm just going to try and predict, like, I'm going to use the words around it, not just the word behind it, right? So it's, anyway, it really is like a heuristic. It's, you know, they just came up with this. It works really, really well in practice. They find that like picking a window size of like 5 is like good enough. Obviously, the larger your window size, you know, the bigger your data set. So you're gonna have a trade-off there, right? Okay, so hopefully that made sense. One of the so I want to skip this thing. So this is, so I'll go back to what I just said. This is sort of important, which is that because you're dealing with words around it, right? Now you're basically, what you're going to look at is no longer going to be like a likelihood, because you're looking ahead at your data, right? So if you remember the way we constructed this all the way in the beginning, right? All the way in the beginning, we had like T of W1, Wn, well, I guess now I call it T. So let's just call it T. T1 to Tn. And then I was like, oh, okay, let's just say this is like P of Tn given Tn minus 1, blah, blah, blah. P of Tn minus 1 given Tn minus 2, blah, 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 and so on and so forth, right? So like that was the original language model decomposition that we had. Then we were saying, okay, if you have a bigram model, then you can basically rewrite this guy as product of Tn minus 1 times P Tn minus 1 given Tn minus 2, blah, blah, blah. And so here now, because you've augmented your data set with words, in front and behind, now you no longer have this nice property that the words you're seeing are actually the words behind, right? So I mean, it's not particularly important, because like we're not actually doing, like, all we care about is like maximizing the likelihood. It doesn't have to be a true likelihood or not, so it doesn't really matter. But that's something to keep in mind. Okay, so I think it helps, and it'll actually help quite a bit when we talk about actually how to implement neural networks, to consider this diagram representation for what this sort of word embedding / word-to-vec model looks like in practice. Okay, so this is basically, a diagrammatic representation of what these word-to-vec models are doing. And so we're going to work through this diagram, as I think it sort of helps to sort of see what actually is going on here. Okay, so let me see if I can put them all onto the same page. Maybe not. Okay, I'm gonna make this a little bit smaller. Okay, so what is our input? Our input is basically this one hot encoding so one hot encoding of our context, right? So X here is a vector, it's just a one hot encoding of the context. So that's just, this is a R to the V vector. Okay. And now, and all that's going to do is that's going to basically extract the particular row or vector or column of my embedding matrix, right? So we're going to have basically here a matrix now. This is going to be V. This is going to be a D. So this is R of V times D. I'm going to call this basically my matrix W, right? So, and then I'm going to write this as H, right? So H is going to be in R to the D. So, okay, so what am I saying here? Basically, the first, the first way you should think about this is you're going to basically construct a hidden layer, right? You're going to do this operation where H is W transpose times X. Okay, so I'm given my X. X is a one hot encoding, right? So it's an R to the V. It's basically a 0 vector with 1 that corresponds to the index of the word that we're dealing with, right? Remember, that's the context word. Then I have my WT, right? My WT is a V by D. And so if I do WT transpose times multiplied by X, essentially what that's doing is that basically is extracting the particular context word embedding, right? But I want to write it like this because it's sort of helpful, because in the future, like when we look at more general neural networks, this is sort of the infrastructure that will be how we do these things in deep learning. Okay, so now H is, you can think of it, so we call this often like the hidden layer, right? So H is this intermediate vector that we're going to construct from our input, right? Now, what do we do with H? Well, what we have is we have another matrix. This is going to be W prime. Actually, W prime is the same as W because, as we said, the context and the words themselves are going to be the same. So here we have, this is going to be V by D now. So, oh, okay. Also, this, for some reason, they call embedding and context a little bit different from the way we do it. Okay, so what we're going to do now is we're going to basically hit out H layer to get Y's, right? Y's here, and then so here we have Y. Well, okay, so hold on. I'm gonna call this P first. P is basically W prime, which is the same thing as W, but I just want to write W prime because it's for a different setting here. W prime transpose H, right? So basically we're sort of like doing this sequentially. So we start by first hitting our index with the first matrix to get H. And then the next step is to start with H, and then I'm going to hit it with the W prime to get P, right? Then to get Y, we're just going to do softmax of P. Okay, so I'm being very like slow about this because what actually is going on is that P, the Cth index of P is going to be, okay, so let's write this. P is a vector in RV, Y is also a vector in RV. The Cth entry of P is actually just going to be WC transpose W. Right. So, sorry. So what I'm doing here is I'm trying to calculate C given W. Right. So this is going to be my W guy. And I'm going to pick the Cth word here. So what I'm saying is that, this is the same thing as what we had before, where essentially what we're doing is we're calculating what the scores are. And how do I calculate the scores is C inner product with W. Okay, sorry. Yeah, so here it's, I've been a little annoying again by changing C with W. I think it should be W and C, but I'm not going to change that. So yeah, so here I've called the word that I'm predicting C and the word that I'm conditioning on W. Okay, and then, right, so then to get back to what we know, right, so P of C given W is then just going to be the softmax, right? So that would just be W transpose W over sum over I from 1 to V X WI transpose W. Right. So this is a vector. I'm saying this is the Cth entry of that. How do I get the Y, which is the output? That's just going to be my softmax. I had a feeling. Yeah. Yes. I know this is confusing. Yeah, okay, fine. Let's call this X. No, Z. Let's call this Z. Uh-oh. Sorry. Okay, I was being lazy. this is Z. I'm conditioning on the word Z, Z, Z. And W here is the embedding. I guess you could also call it phi. That would also be appropriate. Does Y come from the empirical distributions of words given a context? So what I'm not so okay, so what am I looking at here? Here all I'm looking at is this particular model, right? So suppose I have already ran this a while and I have a existing set of predictions for my W, right? Right. So W here is this right. So the parameters are all here, right? These are the parameters. And so essentially what we're saying is that suppose I have some estimate of this, how do I then, what does my model predict for the word C given Z, right? Remember, what is a model? The whole point of a model is to assign a likelihood to the possibility of seeing C followed by Z. Obviously in the skipgram thing, so actually C doesn't have to be followed by Z, but let's forget about that for now. What is this model doing? All this model is doing is assigning a likelihood to this particular case, right? So how does it do that? It basically starts by looking at the Z that you picked. It's going to extract that word embedding. It's going to take inner products with the C you're trying to predict, right? Take inner products between those two. That becomes your score, and then so the Y here will then correspond to basically the probability here. So okay, I am being a little. Now that I see this now that I see this diagram, I realize it's actually confusing. So I sort of want to hide it. The Y, actually the Y, what Y should be is, okay, so, okay, this is, sorry. If you think about what we're doing, right? If I give you, okay, so one way to think about this is I have input, and the input is, let's say, okay, so I'm gonna stick with the CZ pairs, right? So these are the CZ pairs. And you can think of input as basically Z, right? And what's the output? The output is going to be a distribution over my vocab, right? So if you think about what we're doing, remember the whole point of a general language model, okay, so in this word embedding model is that I want to be able to predict, I want to assign probabilities to words. And the only information I'm going to give you is the previous word, right? So in this case, X is sort of like the previous word, and the output, it's not Y yet, but the output is going to be a distribution over the vocabulary, except the data that we see is one particular choice of vocabulary, right? So I feel like I'm not, okay, sorry, I'm sorry. I'm not doing a particularly good job of explaining this. And it's sort of, I mean, this is basically, you know, how machine learning works. What we're doing is we're trying to train a model, right? And it's going to take this X here as its input, right? And it's going to basically, so the X here as its input, what is this X? This is just the context, right? So I guess I should have called this Z, but yeah, okay. So the X is the vector form of this Z, right? And the output of this is going to be a distribution over my vocabulary, right? The thing is, the data itself is obviously just going to be one point, right? It's going to be one. When I train this, how do I train this, right? The way I train this model is that, you know, I'm given a CZ pair, right? And I put Z here, I blah 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 blah, and I get out this this likelihood, right, for all particular C's. But then I actually, so my actual training is one particular C, right? So okay. So in particular, what I'm saying here is that let's suppose I just give you real words, right? You know, right? Sword and stop, right? So how do I actually go about training this? Well, how would I hypothetically go about training this is that I would basically, you know, have the word stop. I would represent it as a one-hot encoding. That would be my X. I'm going to hit it with WT to get H. I'm going to hit it with WT. I'm going to hit H with WT to get my P's, which is basically this. Then once I have the P's, I'm going to basically do a softmax to get a probability I assign to each word in my vocabulary, right? And again, what does that mean? That basically tells me my current model, if I were to have the previous word to be stop, what am I going to assign the next word's probability, right? Then the way I'm going to train is that I know that actually the word in my training corpus is sword. So then what's going to happen is I want to now sort of update the weights to represent the fact that actually I should be increasing the score for sword, right? This is how you train, right? You look at your data, and then you update your model given the information that you saw, right? So I guess what I'm trying to say here is that there's sort of a few things you can think of where like you sort of have your model and your model have your prediction for your model. You can sort of think of it as like an f of x here. This is like the f of x, and this gives you a distribution, but the actual data itself is y. So okay, so I don't want to call this y, because usually when we think of y, we think of the actual training itself, right? So here we here you can think of it as actually you have an f of x, right? These are like the probabilities 0.3, 0.01, blah, blah, blah. And then y is actually, well, just one of them, right? That's my training data, right? And so the way I use my training data is that then I just, I run SGD, and intuitively what's going to happen is that it's going to increase the weight of this guy and then decrease the weight of everything else, right? Because I saw this data, I should expect that this probability should be increasing. Okay, sorry. Okay, let's pause for 10 seconds while I read. Yeah, so okay, so the question here is, why do I write W and W prime? I'm only writing W and W prime here because I want to be clear which thing I'm doing. So actually W and W prime are exactly the same. So but it's sort of, so the W prime helps me to remember this is the matrix for the context, or the matrix for the actual word I'm trying to predict. Okay, so we're actually going to see basically the same thing later on when we look at recurrent neural networks. I don't, okay, yeah, I apologize. I feel like I didn't do that good of a job. Because there's, mainly because this diagram I realizes actually annoyed me. And so my terminology was a little bit off. So the way you can think about this is we have data X and Y, right? And in fact, the data X and Y is going to be the words, right? So well, sword and stop, for instance, right? So usually when X and Y, you think of the input and output. And so really what we're doing is we start with an X, we get an f of X. I mean, we should really call this P of X because it corresponds to like probabilities. And then once we have the f of X, then we're gonna like, compare that to Y, right? I mean, this is the general idea about like, how do you do this training? Well, then we're gonna define a loss function that relates Y, f of X to Y. That's the whole logistic loss that we had before, right? Okay. So what's the hidden layer neural network interpretation of H here? Yeah, so why is this called an hidden? Why is this called a hidden layer? Essentially, you should think of this as, it's a bit like intermediary steps, right? Because if you think about what we do with logistic regression, right, what happens is, well, so I start with my X, I'm gonna hit it with like, okay, well, so it could be WX plus B, right? That could be one way. So given an input, I'm gonna hit it with WX plus B, and then I'm gonna actually, and then I'm gonna call this, well, so here I'm gonna, and then I'm gonna basically do a softmax on this thing, which I'm gonna call equals to F, right? And I basically take softmax to then get back something like P, right? So this is sort of a more general version. Yeah, so right. So if this is one way to think about the logistic regression, is I have an input, I'm gonna basically do a linear transform of this input to get an F. Then I do a softmax to get the P, and P is my output, right? P is like my f of X, so to speak, right? Here, what we're gonna do is we're gonna basically, how hidden layers work is that you're sort of basically you're gonna have like WX plus B, right? I'm gonna call this H, and then I'm gonna actually do it again, and I'm gonna do like a W prime H plus B prime. And then I'm gonna take softmax of this worst thing I call F, and then I get P out, right? So all a hidden layer is that it's like an intermediary step where you don't really see anything, right? It's sort of something that you have a first step, and you run and you take a linear transform, and then you have a hidden layer, and then you do something again. Usually, as we said before, usually what happens at the hidden layer is that, well, okay, I don't know if this is going to make things even more complicated, but usually it's at the hidden layer, you'll have a nonlinear activation function. Okay. We'll see this when we look at when we go to neural networks. But maybe it was more complicated for me to actually go through this. I usually do it backwards, where when I talk about neural networks, and then I give this as an example, I now sort of regret trying to do this first and then introducing neural networks. But I think, I hope that, sorry, yeah. So it got complicated when I started to change y and f of x. But I think now it should be fine, in the sense like all we're trying to do is like a neural network is basically a function, right? It's a function that maps the word to a probability distribution in my vector, in my vocabulary, right? And then, it's parameterized by those word embeddings, obviously. And so how am I going to learn this? I'm going to basically do training with essentially something like logistic regression. Okay. So there are some key points here, and hopefully this will be clear. This guy here is where a lot of the action comes in, right? So if you think about how this is going to work, first of all, if I want to calculate this expression, right, I need to basically know every single embedding, because I need to sum over all the embeddings. And if I have a humongous vocabulary, and if I'm dealing with, say 200 dimension in my embedding space, this is going to be actually pretty expensive, right? So here, what's going to happen is that basically, if you look at your homework, they're going to basically do some approximations where you don't actually have to calculate the denominator here, right? Because if you think about what we're going to do is, in order to train your model for a particular x, you have to calculate f of x, right? Because I need to know what my existing model is, and I need to correct for it, right? But in order to calculate f of x, f of x is basically this, right? So then I need to calculate every expression in here. And so as a result, this is pretty ugly, right? So what happens is that they basically sidestep this and calculate a different expression that means that you don't actually have to calculate the whoopsies. You don't have to actually calculate this denominator, because this denominator goes through my whole vocabulary. So if you look at the homework, you'll see that what you're going to do is you're going to calculate basically exponential of WC transpose WZ over 1 minus that, right? So it's basically going to be an approximation. Okay, so then, all right, so okay, yeah, and then negative sampling. I feel like we probably don't have time to discuss. Again, I sort of worked through this in office hours a little bit, but you can sort of describe negative sampling as sort of basically sort of randomly sampling from a word that you didn't see in your data. And so basically, instead of actually going through every single word in like here, because in my denominator, I actually have to normalize by every single word that I don't see. What you're going to do is just basically going to randomly sample from words that you don't see. So like the intuition here is that you're, what are you trying to do here, right? So intuitively, if I see a 1 here, what's going to happen is when I run SGD, I want ideally what's going to happen is I want this guy to increase and I want all these guys to decrease, right? But what does that mean? That basically, if you think about what f of x here is, f of x here corresponds to the inner product between WC and WZ, right? So, okay, so let's not look at f of x, because f of x actually contains this guy, so that makes it even more ugly. Let me give you another example. Okay, so and this is mainly just for intuition, right? So what we have is we have what did I call it here? I guess I called it P, although P is not great either. So P of x. Okay, so P right here is, well, is the scores such that P of C is basically the WC transpose WZ, right? So it's the inner product between C and Z, where our data looks like C and C. Okay, so this is the scores. In particular, you could think of this as, you could think of these as numbers. So it's like, 0.3, 24 minus 10, blah, 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 and so forth. And then what I get out is I get out a y, right? Wait, so here I have an f of x. I have an f that converts my p to this guy is a probability distribution, right? Probability distribution, but I'm actually going to ignore this layer because you have to do the softmax layer. So what I have is a y, and this is going to be like 1 0 0 0 0, right? So this is the actual word seen, right? So in particular, this is the z, right? So that corresponds to the z. And so what the intuition here is that, like, if you think about what's going to happen when you have SGD, right? My model is my current model with the current word embeddings, right? Remember, these are parameters. My current word embeddings, this produces this score for the words in my vocabulary, right? But then I see that this C, the actual data is Z, right? So intuitively, what should happen, that should mean that my score here should be increased, and the scores naturally down here should all decrease, right? Because you're sort of, what you're doing is you want to upweight this guy, right? Because why are there? Oh, sorry. Okay, you want to upweight this guy, and we can work through. We're not going to work through actual SCD, but that's essentially what you do if you just run SGD naively, right? What's going to happen is that these parameters are going to change in such a way that the score you assign to Z gets increased and the score you assign to everything else gets decreased, right? But that is going to be really, really ugly. Why? Because I have to change my weights in the sense that I have to change every single WC, right? Because remember, what is this? This is basically W1. This relates to W1, W2. This, and every P here just corresponds to the W that it's indexed by, right? What that means is, in order for me to increase this guy here, all I need to do is increase WZ. Or I'm sorry, I don't need to increase WC. I need to change WZ such that it better aligns with WC, right? At the same time, I'm going to change every other W such that it aligns a little worse than WC, right? I guess, right? So yeah. So at a high level, what's happening is, right? Remember what we're trying to do is we're trying to figure this out such that like the inner products of things are going to match, are going to be close for data sets that we see, word pairs that we see, right? And if you run SGD, every single time you run SGD, what's going to happen is it's going to see a pair, and then it's going to want to push those two vectors closer together, but then push every other vector further away, right? But then that means it needs to touch every single vector in your embedding matrix, right? And that's just a lot of work, right? These things aren't going to change too much, right? Because you have like v minus one of them. So the change that you're going to make with W1, W2, WV is going to be very, very minimal. So you'd rather not change them too much. And so what the heuristic that they do is they basically say, I'm not going to actually, every time I run SGD, I'm not going to update every single W1, W2 to WV to decrease the score of it. I'm just going to randomly sample K of them and decrease their score. So that way I only have to change K word embeddings every single time I run an SGD. Does that make sense? Right, sorry. I think I got lost in the math. Right, so let's take a step back. Okay, so we have our data is basically word pairs, and we have the left data is sort of our the input, the sort of the data we're trying to guess, and the right one is the word that we see, and we want to make it such that the parameters of our model, which correspond to the word embeddings, you learn the model in such a way that the word embeddings for these two words are going to be close if I see a lot of these words in my data, and they're going to be further away if they don't appear in my data, right? So when I run SGD, right, what is SGD? Basically, that's like running gradient descent on one data point at a time. When I see one particular word pair, what's going to happen if I don't do anything smart is that it's going to move the words closer together to the context because I see them together. And it's also going to move every other word further apart, which then means I have to change every single parameter in my W matrix, which is a V by D matrix. And that's just expensive. So one trick is I don't want to change every single W1 to WV here. I'm only going to change K of them at random. And so that gets you quite a considerable amount of saving in computation. Again, it's a heuristic, but it seems to work out pretty well. Is this just the dropout technique in neural networks? So, I mean, it's not particular. It's not particularly the same thing. It has sort of the same flavor to it. I don't think it's exactly the same. And I assume most of you don't know what dropout is, and so we're not going to talk about this. But yeah, so it has a very similar flavor to the dropout technique, which is basically something you can do with neural networks. But yeah, so okay, that's all I'm going to say about that because we're not going to talk about that just yet. Okay, any questions? It was way harder than I was expecting. Okay, so we have okay, so I'm actually going to skip analogies because you guys have seen this. It's always fun. I feel like it's fun for me to be the first one to tell you about this, but now I assume you guys know what it is. It's basically vector analysis with word embeddings, and it's really cool that these things actually work really well. I guess one thing I do want to mention is that word embeddings, I mean, I was meant to write a extra assignment on this, so maybe I may still do it. Obviously now we have UP, so who knows. But like word embeddings is not surprising, because if you think about the way word embeddings work, it's going to work on a humongous corpus. And as a result, it's actually going to pick up on all the biases that we humans have in the way we talk and in our literature. And so it's interesting and like something important to note about the fact that these word embeddings are actually a very accurate representation of, you know, humanity. So the way we write stuff, we're obviously biased in terms of certain things, and that is reflected in the data as well. Okay, so here we're going to, so I'm going to gloss over this because it's not particularly important. Word2Vec, as I said, so the thing we just talked about with like the skipgram and negative sampling, that is essentially what Word2Vec is. Then people came along and tried to make it even more computationally efficient. And so that's what GloVe is. And so you look at GloVe as well in the homework. Essentially, it's a very similar, you know, thing, except there are even more computational tricks. And it seems to do a little bit better, and it's just way faster to train than Word2Vec. So the actual like specifics of this model, you know, they're not particularly interesting to me. Like I think these are just different ways to do a similar thing, using, you know, coming up with different computational hacks to get better performance. Okay. What I do want to talk about, which is the sort of the last part of the homework, is this idea of thinking about how to visualize embeddings. Okay, so this is actually a very general thing, because now when we think about machine learning, you know, big data, you have high dimensions for many things, right? In this particular case, right, we're thinking about these embeddings. They could be 100 dimensions to 300 dimensions, and you know, we looked at analogies, and that's one way to think about, okay, does this actually make sense, right? You can calculate perplexity, but as we said already, the whole point of word embedding is not to, you know, make my language model as good as possible, is to actually have word embeddings, right? So one way to sort of measure the performance of it is to just check it against your intuitions about like analogies. And surprisingly, it worked really, really well. But the other way to do it is like, you know, we like visualizations, right? We want to visualize these, but obviously they're in high dimensions. So it's not that easy to, you know, to sort of visualize this. So what we want to do is we want to basically do some type of dimension reduction procedure that allows us to represent these things into like 2, maybe 3 dimensions, so that we have some better intuition as to what is going on. All right. So I assume everyone's first guess here would be to use something like PCA, right? So PCA is essentially a dimension reduction procedure. You know, we didn't talk about this in this class, but the key point about PCA is that it's a linear method, right? Whereas what we're going to be dealing with is this really, really high dimensional structure, and we do not think there is a linear representation of our data, right? So we assume there's actually somewhat like non-linear low dimensional manifold that these word embeddings lie on, right? You know, it could be sort of like a, you know, something like a unit sphere, but it's going to be a little bit more convoluted. Maybe there's some sort of like, you know, bumps and stuff, but it's definitely not going to be like a linear structure. Okay, so the key point here is that we need to actually have a nonlinear method to get about finding to you know, to basically represent our data, and so we can't use PCA. So how are we going to do this? It's actually it's I mean, it's sort of cute. It's pretty straightforward. The math seems pretty complicated, but it's actually pretty straightforward. So let me just tell you what the intuition here is, right? We're actually going to turn this into a machine learning problem. And how does this work? We're basically going to, okay, so intuitively what you're trying to do is you have your word embeddings, right, in this high dimensional space, and you're going to associate every word embedding with a point in two-dimensional space. Okay, so here the y's corresponds to the points in two-dimensional space. Right, so to give you a graph, oh la la, I always do this the wrong way around. Sorry. So, you know, in this humongous, this is my sort of, you know, word embedding, and I'll have phi w1s, phi of wj's, right? So this is in like r to the d, and then what I'm going to have is I'm going to have basically like, think of like some square, and I'm going to have like yi's, yj's. This is in r to the r2, right? So with every word vector, I'm going to associate it with a point in R2, right? So the question then is, well, how do I, so basically you should think of these y's here as parameters, right? It's like doing word embedding all over again, right? Remember, the way we thought about word embeddings is that these are parameters and we're trying to optimize these parameters. And so you do the same thing here. Now you basically treat, like, these are now given, right? Because we have the word embeddings, and then we basically treat these y's as parameters, and we're going to do some optimization to learn these y's. You know, then we have to think about, well, what's the optimization we want to do, and that's where the TC model comes in. Okay, so what we're going to do is we're basically going to have two distributions. One of these distributions is going to measure the pairwise similarity of these word vectors, word embeddings, and it's going to, and you're going to have another distribution that measures the pairwise similarities of these embedding vector, visualization vectors. Okay, and so once you define two distributions, right, I can then measure how close these two distributions are, assuming the set that the distribution's on is exactly the same, right? So what do I mean by that? You know, if you're thinking of like in R, just R1, right, you could have a normal, and then you could have something that looks like this. You might be thinking about, well, how close are these two distributions to each other? And so there's this measure, you can define these measures that basically measure the distance between two particular distributions, right? So intuitively, you might say that, you know, obviously these two purple distributions are closer together versus this purple one and this green one here, right? And so you can basically look at what is known as divergences that measure the distance between two distributions. The key point is that the distributions must be, you know, on the same sample space. What do I mean by that? Basically, what is a distribution? A distribution assigns probabilities to things, right? Here, I'm just assigning probabilities to numbers in R, right? From negative infinity to infinity, right? So this is from negative infinity to infinity. And probability is assigning numbers to that, right? Probabilities to numbers in minus infinity to infinity. Here, the issue is that the most obvious thing I want to assign probabilities to would be assigning it to the actual vectors themselves, right? But the problem is that the vectors themselves, oopsies, the vectors themselves, they lie in two different spaces, right? And then you cannot compare distributions that lie in two different spaces, right? I can't define a distribution in RD and compare that to a distribution in R2. It just doesn't work, because, you know, you're operating under two different sample spaces. That's what it's called. 241, 242, I forgot where. So what you need to do is you need to be a little bit clever about it. And so what you end up doing with this t-SNE algorithm is you basically end up defining the sample space as pairs of ij. So I'm going to be a little bit clearer here. Well, okay. So the intuition is I'm going to basically define probabilities with respect to ij. How am I going to do that? First of all, what I'm going to do is I'm going to basically calculate this. What does that mean? What that means is this is basically a Gaussian kernel. Again, sorry. So there's a lot of pretty complicated stuff that I have a feeling people might not really understand here what I'm talking about. What is a Gaussian kernel? Basically, you have a center, right? So this, you can think of it as the mean, and you basically put a probability distribution around it, right? So in this case, I'm going to create a language model. What is a language model? I'm going to assign probabilities to words around. I'm going to assign probabilities to words in such a way that if phi of j is close to phi of w, if phi of wj is close to phi of wi, then I'm going to assign a high probability, right? So and the way I assign the sign probability is as a Gaussian. So if it's very close, I'm going to assign a higher probability. As I get further and further away, it's going to assign a lower and lower probability. Okay, so that's basically what I do. I can basically create this pj given I, right? By doing this normalization, and hi is the bandwidth. Hi corresponds to, you can think of it as like how fat the Gaussian kernel is, right? Okay, the Gaussian kernel is, it basically what it is like I have a point here, and I basically put a normal distribution like in that space, such that I assign probabilities related as if you were drawing from a normal random variable with that in the center and with a particular variance. So that's sort of the idea. What it ends up being is that you're basically going to assign probabilities, right? J given I, you're going to assign them higher if the two word embeddings are close together, right? And so, and that's really what you want, right? If you want them such that if P of J given I, you want this to be a big number if Wi and Wj are close in their space. Okay. So then what we're going to do is you're going to basically create Pij as a symmetric version of Pj given I of Pi given j. Okay, so what does that mean? So Pij is a number, and it's indexed by ij, right? And intuitively, what is Pij? It's sort of a measure of how close Wi and Wj are to each other. There's a reason why we don't just take the distance. I don't have time to explain that. Then what we're going to do is we're going to have it such that we're going to create another probability distribution, Q. This is again indexed by ij, right? Ij is just in v squared, right? So ij is in v squared because it's just two indexes correspond to my data. And basically here, I'm going to have it such that yi and yj, if they're close together, then they're going to have a high distribution again. Okay, so then what happens? Okay, so the specifics of this are not that important. You can look through this later on. Basically, what we've done is we've defined two distributions, right? Qij is a distribution such that yi and yj, such that yi and yj, if they're close, then the probabilities that are assigned to the ij index is going to be large. And it's the same thing with pij, right? If wi and wj are close in the word embedding space, then pij is also large. So intuitively, what we're trying to do is we're trying to create two distributions indexed by, this is a weird thing. We're indexing by the pairs of vocab in our data, right? So all possible pairs of words, and then we're going to this pij is already fixed, right? Pij is just going to be defined as this. Intuitively, it's defining a distribution such that pij is large if the word embedding associated with I and the word embedding associated with j is large. Then what we want to do is we want to learn, remember these are parameters, we're trying to learn yi and yj such that the distribution defined on qij ends up being very close to the distribution defined on pij. Sorry for going over. Okay. I sort of wanted to finish this topic because I guess we're going to new topics later. Yeah, okay. But I feel like I sort of sped through that, unfortunately. Okay, questions? Whew.
I have a question about the homework.
Sure.
Could you explain what like singular value decomposition is?
Okay, hold on.